Hello everyone, I'm Haoyi. Today I'm gonna present my paper Inverse Entropy, a fully probabilistic framework for uncertain quantification in language models. These are my amazing collaborators Ruihan from University of Minnesota, Naichen from Northwestern University, Lai Fan from University of Illinois, and Raed Kontar from University of Michigan. The first question is, why do we need to quantify uncertainty? I think everyone watching my videos now used the ChatGPT before, and we all know large language model can make mistakes. For example, if we ask Google how to deal with cheese not sticking to pizza, Google will tell us add some glue. And also large language model can easily hallucinate, which means producing some confidently wrong outputs. For example, if we ask ChatGPT to do some literature review for us, a lot of times we find like the literature they provide for us doesn't exist at all. It's likely just make them up. So it's really important for us to understand how much we can trust an answer or not, especially in some high-stake applications like healthcare, legal, or autonomous systems. And now a lot of people, they try to use uncertain quantification to enable large language models to acknowledge their confidence in a generated output. For example, if we have good uncertain quantification method, it will tell us the output add glue has high uncertainty, and then it can help us to do the downstream application like selective prediction. The high uncertainty will serve as a feedback to the large language model generating process. And the large language model will refuse the original output add glue. Instead, it will generate the answer I don't know, or it will search online. If we do it in this way, it will help to improve the reliability in the output much more. And what exists in the literature? Basically, there are two categories. The first category is token probability methods. It's because every time one large language model generates the next token, this token is sampled from a distribution, and each token has its corresponding probability. But the problem of these methods is a lot of times we do not have access to the probability because most of the models we are using now are black box model like ChatGPT. And also the probability can be misspecified. And for the sampling-based method, it takes the idea from sampling in statistics. Basically, if you ask a large language model the same questions multiple times, it will generate multiple answers. And if these answers, they are really similar from each other, we can say like they have low uncertainty. But if these answers, they are really different from each other, we may assume they have high uncertainty. But the problem of the sampling-based methods is they are usually heuristic and they lack of probabilistic foundation. And both these two methods, they miss confidently wrong cases. And our goal is to deal with the limitation in the existing literature. We want to develop a fully probabilistic framework to quantify uncertainty in language models, which means we want to model the input as a random variable and also the output as another random variable. And then we build the jointly distributions on these random variables, and then we can get the uncertainty based on these distributions. Our main tools are perturbation and dual random work. First, let me use an example to show you guys why do we need perturbation. This example is the confidently wrong case I just mentioned. If we ask the question which contract Anna signed, large language model will give us all the same answers. If the answers are all the same, we may assume they have low uncertainty, but actually the answers are incorrect. And after we apply perturbation to the original questions, which means we change the way to ask the original questions a little bit, we will find much more variability in the generated outputs. And it shows that perturbation can capture the hidden uncertainty we cannot get if we just ask the same question multiple times. And we also use a theory to show why do we need perturbation. First, please look like these two plots. It shows the level size under the ground truth function and also the large language model functions. For the ground truth function, if we perturb the original questions a little bit, but we do not change the semantic meaning, after we apply the ground truth function, it will generate us the same response. But large language model is not usually accurate. So even if we ask the perturbated inputs with the same semantic meaning, maybe it will generate different outputs. And it shows that the perturbated inputs, it may lie in different level sets under the large language model function. And we showed that the variance of the outputs from the perturbated inputs generated by large language model actually is a function of the misalignment between the ground truth and large language model, which is the uncertainty we want to quantify. So now we have an original input and we have its corresponding output. And we apply perturbation to the original inputs. We get a lot of perturbated inputs, and we apply large language model. We get corresponding outputs. So don't forget our goal. Our goal is to build fully probabilistic framework. Now the goal becomes like we want to define the distribution Px supported on the point x0 to xn, and we want to define the distribution Py supported on the output points y0 to yn. And also, we want to model the relation between the input and output space using the distribution Px given y and Py given x. After we have these distributions, we can define the uncertainty on these distributions. And in the following, I want to show geometrically what makes uncertainty different. So please look at this plot. It shows the relative location of the points in the semantic space. The first line shows if the inputs, they are really close to each other, but the output, they are really far from each other. It will indicate this question has high uncertainty. But if the input, they are really far from each other and the output, they are still really close to each other, we can say maybe the question has low uncertainty. But there are a lot of different possible similarity structures in the semantic space. And what we want to do is we want to model all the possible similarity structures in the semantic space. We can use the defined probability to model it. And the probability defined principle is we want to assign higher probability to the dense regions in the semantic space. For example, in this plot, we will assign the y3 the highest probability, y2 the lower, and y1 the lowest probability. And to implement this principle, we can use this equation. Look at this fraction. This fraction means for the point yi among all the possible neighbors, how close yj is to yi as the neighbor of yi. And then we take average over I. It means if yj is a commonly close neighbors to all the points, and which means yj is in a really dense region, we can assign yj a higher probability. It's just like the principle I described. It has a really beautiful interpretation in random walk language. We can treat the closeness of yj as a neighbor of yi as the transition probability from yi to yj. Because if for yi, yj is a closer neighbor, of course it's easier for yi to transit to yj than any other points. So we model y0 to yn as a random walk, and we define the transition probability, use the fraction in the last slide. And then we can also involve a uniform vector, and we can rewrite the equation pyj use a random walk language. And I will describe you guys what is this uniform distribution means. The uniform distribution means we can start from each point with the same probability, because the probability Py is equal to Yj means we can start from each point in the output space, and from that point, we can transit to Yj. And the uniform distribution means the probability to start from each point is the same. And we can transit from I to j, k to j, j to j, n to j, and after we add them together, it's the probability Py is equal to Yj. And after we define the random walk on the output space, similarly, we also define a random walk on the input space, and we use the same way to define the transition probability in the output space to define the transition probability in the input space. So now what we have is two random walk, one random walk in the input space and one random walk in the output space. But we know these two random walks, they are not dependent, they are not independent. We want to model the relation between the input space and output space. So we need to find a way to connect these two random walk together. And there is a natural way. Large language model correspondence, because don't forget, each output yi is generated from its corresponding input xi. So this large language model correspondence can help us connect these two random walk. And now what we want to do is we want to use the random walk to define the distribution px given y. So first, what is the distribution? The probability Px is equal to xi. It means we can start from each point in the input space to transit to the point xi, and there are different transition probabilities. But the prior is yj, which means we have a prior. The prior is no longer uniform. It means the probability to start from each point is no longer the same. So given yj, to define the transition probability of xi, it becomes like that. First, if we want to transit from x0 to xi, the probability to start to transit from x0 is actually the transition probability from yj to y0, because intuitively, if given yj, y0 is really close to yj, means also x0 is really close to yj. Of course, it's easier to start from x0 to xi. So we can also start from xi to xi, and we can start to transit from xk to xi. We can also start to transit from xj to xi and xn to xi, and we add all of them together, we get the probability pxi given yj. So now we have already had the probability Py and the probability Px given y. From these two probabilities, we can use the simple statistical theorems to get the probability Px and the Py given x. And I want to highlight our contribution. Our contribution is not only define one uncertainty measure for the large language models. What we do is we define a fully probabilistic framework, and we can let the community to define any uncertainty measures they want to define based on our probabilistic framework. And it provides the community much more flexibility. For example, you can define the entropy-based uncertainty measure, you can define the divergence, you can define the distance based on these distributions. And the uncertainty measure we choose is the inverse entropy. We all know the entropy can help to capture the uncertainty, but why inverse? So this picture shows the hy given s can help us to capture the uncertainty, because if inputs are all the same, we can use the randomness difference in the output space to get the different uncertainty. And also if outputs are all the same, we can use the difference in randomness in the input space to get the different uncertainty. But the reason we choose the inverse direction because it has an additional advantage. For example, if the output contains really limited information, let's say multiple choice questions, maybe the outputs are all A. And at that time, how can we distinguish the uncertain difference between the questions with the same outputs? We can look back into the input space. At this time, the input space difference can give us much more information about uncertainty. And here is our experiment setting. We have 3 data sets, including Q&A data sets and also multiple choice data sets. And we also implement a lot of SOTA baselines, including semantic entropy is a measure published in Nature, and also a lot of different baseline models. And we also have 3 different evaluation metrics, including AURC, PRR, and BRIER. These 3 metrics, they all calculate the misalignment between uncertainty and correctness. And now we have the experiments. We can say our method achieves SOTA for all the data sets under all the evaluation metrics. But don't forget what I just mentioned. These 3 evaluation metrics, they all calculate the misalignment between the uncertainty and the correctness, and which means it has a latent assumption the uncertainty is related to correctness, but in reality, it's not always true. And a lot of times we do not have the correctness label in the data set. So we define a new evaluation matrix called TSU to provide the community a new evaluation matrix free of correctness label. Temperature is a hyperparameter to control the randomness for large language models to generate the outputs. And if we increase the temperature, the true uncertainty of the answer will also increase. But how about the uncertainty? How about the uncertainty we define? Which means the estimate uncertainty. If the estimated uncertainty also increase as the temperature increase, we can say the estimated uncertainty is just like the true uncertainty. It has a really good performance for the uncertainty quantification. So we define a new evaluation matrix called TSU. It calculates the percentage of questions in a data set, like satisfies the role as the temperature increase, the uncertainty increase. Here is the formal definition, and the advantage is it's free of correctness labels. And these are the results for TSU evaluation matrix. And we can also find our method inverse entropy achieves SOTA and much better than other evaluation matrix. And here's our contribution summary. I'm Haoyi. I'm really glad to present you today. Thank you.